You learned about the diode in the previous chapter, which is a p-n junction. You take a p material and join with an n-type material, you get one p-n junction, then you have two terminals outside. That's the basic diode construction. For a transistor, there are three layers, not just p and n. You can have a transistor in two different types of construction. The first one is PNP. So you see two types but three layers. An N-type is sandwiched in between two P-type materials. Or you can have another construction known as NPN. Two N-type materials, they surround a P-type in the middle. In the BJT, three terminals are the different input and output. They are named or labeled emitter, for short is E, base terminal for short is B, and C is for collector. Most of our course is focused on this NPN type. All the examples, problems, exercises, they focus on NPN type. The difference between PNP and NPN is in the construction, and the direction of the current and polarity of the voltage will be exactly opposite. So what you study for NPN, if you mirror that, just flip it for PNP, that would be the way to do that. And why the name bipolar? There are two poles. One, is the electron, which is negatively charged, and the other one we call hole, which is positively charged. So both the holes and the electrons, they participate in the current flow, in the injection process in oppositely polarized material. That's why the name bipolar junction transistor. So this one is an example of a PNP transistor. You see there are actually two junctions. The left junction is a PN junction, and then you have a right-hand side junction NP. If there are three layers, you have two junctions. Also, you see the black area. One is quite thin or narrow, and the other one is wide. What do we call this region? Do you remember the name of the region? What is the name of the black region at the junction? It is called the depletion region. You learned that from chapter 1 and 2, mostly from chapter 1. Why is the black line on the left-hand side narrow and why it is wide on the right-hand side? Look at the junction, the emitter base or base emitter junction. If you take P and N, the polarity of the input DC voltage, plus and minus, this is actually a forward bias. NP junction, minus and plus, this is also reverse bias case. When you forward bias a junction, EB junction is forward bias, emitter base junction. The depletion region is small in a forward bias. Majority carriers will flow, as you can see from the wide blue arrow. And here P and N or NP, P has to be connected to a plus polarity to be forward bias, but in this case it's not, so you have a reverse bias collector base or base collector junction. In the reverse bias, minority carriers have more right of way. You still have majority, but minority carriers will flow very easily. So when a BJT, one side is forward bias and the other side is reverse bias, it is operating in the active region. Also, you can see IE, this is called the emitter current. And then you have some outgoing current as well. The IE is the incoming current into this transistor. The outgoing one, you see IC, collector current coming out of the collector terminal, IB also going away. If you see the whole transistor as a node, this is satisfying the Kirchhoff's current law, which says the current coming into a node, IE, equals the current going out of a node, IC plus IB. So here is a universal formula for BJT transistor. Emitter current IE equals collector current IC plus base current IB. IE equals IC plus IB. In many cases, more than 50% of the cases, you can say IE approximately same as IC. We don't add the IB. You will see later on why that's the case. Now, look at the NPN type BJT. Can everyone see the slide?
Yes.
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 So we just took a different construction. See how the current direction changes. Now everything is going to the left or counterclockwise. If you think of the transistor as a single node, what is coming inside the node? IB flows from bottom to top, comes to the node. IC flows inside. So incoming current is IC plus IB, and then outgoing is IE. Doesn't matter if you take PNP or NPN, this equation that you are seeing on your slide is satisfied. As you can see, this one, different types of bias, polarities have changed. N junction, when you connect with P and N junction will be net positive. So this one is a reverse biased. This one, the left-hand side is forward biased because at the end of N, it will become net positive due to migration of oppositely attracted carriers. So the base emitter or emitter base is forward biased. Here, the collector base is reverse biased. The large blue arrow is indicative of the main current that is flowing through the device, and the small, see, there's a narrow blue arrow that is joining. So base current is joining collector current, and you have emitter. Typically, the collector current is in the range of milliampere, 10 power negative 3, so 1 over 1000. And typically the base current is in microampere, 10 power negative 6, sometimes pico or even nanoampere, almost 1000 times smaller than IC. So if you take an equation, IE equals IC plus IB, IC is in milliamp, IB is in microamp. If you do not add the microamp with milliamp, they are still approximately the same answer. That's why sometimes we can say IE approximately equals IC, but please remember the equation. Then after we talked about the construction, we can see the BJT can be configured in different way. The first one is common emitter. Now we are at the NPN transistor, which means emitter is common. It goes to the ground. As you can see, the E terminal goes to the ground. It is common to the input side. In this case, you have an input current IB with the base terminal is the input. And then it is also common with the output side, the collector side. The output current is the collector current. You have to have the DC sources inside. We call it the biasing, the act of providing the DC voltage so that the transistor can operate. This action is called biasing. We need the DC bias. Also see how it works. IB plus IC equals IE. When the emitter is common to both input side and the output side, we call it the common emitter configuration. And here is the symbol of BJT, bipolar junction transistor. Just like diode and Zener, they have their own symbols. The BJT has its own symbol in the circuit. It is drawn like this. The vertical black line is always connected to the base terminal. The other terminal is collector, and emitter terminal has an arrow. This arrow is going out So you see, IE is going out, IB, IC coming inside. That is for NPN transistor. If you have a PNP transistor, the arrow will be, instead of going out, the arrow will be like this, going in to the device. And what else do you have to change? Can you guess? You have to change the current direction. You have to reverse the direction. So again, you see, IE equals IB plus IC. Incoming equals outgoing. That is for PNP. So whatever I drew now in yellow marker, that is for PNP. But on the slide, you see this is NPN. So after common emitter, what else can we do? We can do other configuration because we have two other terminals. Common base. Now you put the base to the ground. Here is the base. Again, I think I should highlight the base is here on the ground. It is common to the input side here. Now the input is the emitter side. Also, the ground is common with the output side. Collector is the output side. So this is a common base PNP configuration. Notice how IE equals IC plus IB. You reverse every direction and polarity with the NPN. This is the base, which is common. Here, input side, output side. IE equals IC plus IB. Depending on the configuration or orientation, your input and output might be changing. And then here is the symbol. This one is the symbol for a PNP. As you can see, the vertical or horizontal line always is the base terminal. The one with the arrow is always the emitter terminal. For PNP, it's coming inside. The one without the arrow is the collector. If you take the NPN, which is top right, bottom right, sorry, base terminal is here, emitter is an arrow, an outgoing arrow, and collector is a terminal without any arrow. So here the base is common to both input. Emitter base junction is the input now, and output is collector base junction. And the third one, if you have already guessed, will be the common collector. Now we rotate the transistor in such a way that the collector is in the ground. It is common to both the input side, which is B, base, and the output side, which in this case is the emitter. In all cases, the current equation has to be satisfied. So here is a symbol for PNP, and this one is for NPN. Before we move on to the next part, there is one other thing you should remember, which is the nature of BJT. A BJT is a current controlled device. In order to find or get some output, you have to have an input, and the input is a current, which we'll see in the next few slides. Any questions?
No, sir.
Okay. Now here is a characteristic graph. Let me again make it read mode. You have two sets of graph here. One graph is IB, the base current in microamp, versus VBE, the base to emitter voltage. So there's a current versus voltage graph on the right hand side. Also on the left hand side, you have IC versus VCE. And we are assuming this is a common emitter transistor, which means on the input side you have the base, on the output side you have collector. For the diode, if you remember, the diode characteristic graph looks something like this. At 0.7 it takes off. But why are there two characteristic graphs for this transistor? If you want to describe, the reason is, if you want to fully and properly describe the behavior of a three-terminal device such as this, you must have two sets of characteristics. One set is for the driving point or the input point, the input characteristic graph, and the other set is for the output side. Remember, for the common emitter, let's see the common emitter. The input side is the base emitter side. So input current is the base current is the input current. And the output side is collector emitter. CE is the output, BE is the input for common emitter. Remember? On the right hand side, you see the input graph actually. You have to have an input base current IB in order to run the transistor. IB is the controlling input current, typically in microamp. However, you are not going to get any IB, any base current output, unless you satisfy a certain condition for the voltage between base and emitter. The voltage between base to emitter, you see, it is around 0.7. You can see some current output. So what is your guess? What is this transistor made of? Which material? What is the material of this transistor?
Silicon.
It is silicon because the forward bias voltage of a silicon diode or transistor is 0.7. And throughout this course, we only assume silicon transistor. I never asked any problem with other types of BJT. Also, I didn't see in the textbook. So you are clear now at 0.7 volt, you're going to see some current flowing. But there are three different lines here. Each one corresponds to a certain voltage value between the collector and emitter. If you have 1 volt between collector and emitter, you will read from the top line. For 10 volt, you read the middle line. For 20 volt, you're going to read the lowermost curve. On the left hand side, so base characteristic, base is your input. This is the input graph. Collector characteristic, at the collector of a common emitter, BJT, you have the output. This graph on the left hand side, the larger one, is the output current versus the output voltage for a certain level of base current. Let's see again, output current is given in milliamp, and you see input current is given in microamp. And VCE is the x-axis, the voltage from C to E. What are the blue lines, different blue curves? See, 90 microamp, 80 microamp, 40 microamp. Each one corresponds to a certain value of IB. Let's say you find out by calculation that your IB is, where should I take it? 20 microamp. Let's say it is 20 microamp. So you have to do all your reading from the 20 microamp blue line. You can also remember that in the last topic we taught load line. What is the load line? The load line is the black line that is decided by the network by using two extreme points. So at one extreme you have a VCE value. Let's say maybe VCE is, let's say this is 12, and the other extreme you will have a current value. Let's say 4. If you join the point between 4 milliamp and 12 volt, see where it intersects, maybe around here. From this point, if you project a line on the IC axis, you will get the operating current ICQ at Q point. And if you drop a line down, straight line down on the VCE, you'll get VCEQ. There are two gray regions provided on the graph. The left-hand vertical gray region is called a saturation region. We'll see what that means. In a saturation region, you can have a lot of current, but you don't really have an output voltage. And the bottom horizontal gray region is called the cutoff region. In a cutoff region, you will have a voltage appearing between C and E terminal, but there is little to no current. So these are the two extreme points of a load line. One is the cutoff region, the other one is saturation. There are three active regions of the BJT then. Sorry, three operating regions. The first one, the normal one, is the active region. If we go back, the one which is not in the gray area, see, bottom is gray, left hand side is gray. So in the white area within the base current lines, this is the active region. The left hand region is saturation, the bottom region is cutoff. For a cutoff region, the amplifier is actually turned off. You have seen that in cases where you have voltage but little or no current, it's like an open circuit. There's a voltage for the open circuit but no current. Saturation means there's a lot of current but little to no voltage. What does it tell you? It is like a closed switch or almost like a short circuit where you have a current but rarely voltage. And the amplifier is conducting current, it's fully on. And obviously in the active region, the amplifier is on, performing normally. Now I talked about the approximation where IC can be sometimes approximated as IE, because if you take the equation IE equals IC plus IB, now IB has disappeared. Why? If one is milliamp, the other one is microamp, you can ignore the one that is 1,000 times small. It will not change the final value too much. Base emitter voltage, VBE, we always take 0.7 volt for this course, assuming it's a silicon material. There's another parameter known as alpha. It is the ratio of the collector current to the emitter current. IC over IE is alpha. In DC mode, alpha DC is IC over IE. If IC exactly same as IE, just like the approximation, alpha ideally would be 1. However, if you take IC plus IB equals IE, IE is slightly larger. So alpha would fall in between 0.9 and 0.998. Not too much difference. If you are operating in AC mode or doing the analysis in AC mode, you just simply take the delta of IC over delta of IE. In AC, you have a positive peak and negative peak. So there will be corresponding maximum IC and minimum IC at the two extremes, which will also correspond to the two extreme points of IE. You take the difference, that becomes the delta of IC and delta of IE respectively. Important is beta. It is like an amplifying factor or a gain factor for the BJT. There's a relationship between alpha and beta. Alpha is given by beta over beta plus 1. For beta, there is no unit. You'll get a number, maybe 20, 50, 120, 90, whatever. It just tells you how much you can amplify the input current. This is a measure of the BJT. If you rearrange the equation, now the left-hand side shows you alpha in terms of beta. If you rearrange, you can see beta in terms of alpha. It's alpha over 1 minus alpha. Other important relationship, IC is beta times IB. Always remember, this is crucial. You have to remember. Collector current is beta times base current. If you have, say, 20 microamp base current and your beta is 90, so IC is almost 100 times larger than your base current. If you don't have any IB, you will not have any IC. Therefore, IB, the input base current, is the controlling element, and BJT is a current control device. If you take IE equals IC plus IB, you can find the right-hand side equation, because this, if you do it, IB plus beta IB, which means IB plus IC. Now you see another graph for the operating limits. This is an output graph for a common emitter BJT. On the y-axis, you have the output current, collector current in milliamperes. And then you have on the x-axis VCE, the output voltage, which is taken from the collector terminal to the emitter terminal in volts. We have discussed the saturation region, which is the vertical shaded area, where you have a lot of current, but rarely any voltage. And the cutoff region is the bottom part, the narrow bottom part. There are some parameters here. ICEO means reverse leakage current, C to E, collector to emitter reverse leakage current when the base is open. And then you have a VCEO, which is maximum allowable voltage from C to E before the BJT breaks down. So it is a breakdown voltage. VCE set, the saturation voltage between collector to emitter when you are operating in the saturation region. So what is the maximum possible current? That is the ICEO in the cutoff region. Let me zoom in actually. This small amount of current is the maximum current you can see in the cutoff region. So not a lot of current or almost no current. That's what the slide is telling you. VCE is maximum. You'll have a maximum C to E voltage, but minimum IC. If you are in the saturation region, again, you can have a lot of saturation current, IC max. There's a limit, of course. Otherwise, if you don't follow the limit, the BGT will burn. But here is VCE saturation, a little amount of 0.3 volt. The transistor operates in the active region, which is situated between the saturation and the cutoff. The blue lines are different corresponding base current levels, but when you see the shaded black region, the boundary on the right-hand side, it means that at any point on that curve, you are having the maximum allowable power dissipation. PC max, the maximum power output in this case is 300 milliwatt. How do you get it? Multiply the output current by the output voltage. At any point, you see 300. Here is 30 milliamp multiplied by 10 volt. At this point is 300 milliwatt. If you are operating at 15 volts, you must make sure that you never exceed 20 milliamp current. Otherwise, what happens if you go to the shaded blue area? In that area, you are trying to dissipate more heat than is designed, then you will damage or destroy the BJT. That's the limit of operation. Do you have any questions about this one? Any questions?
Not for that.
All right, let's move on. The next few slides, I think, quite like short or quick. This is an example of a BJT spec sheet. What does it say? What is the maximum allowable collector emitter voltage? So shaded in blue, and then collector current given the limit. What is the power dissipation? You see 625 milliwatt at 25 degrees Celsius. If your operating temperature is above 25 Celsius, for each degree Celsius increase, you have to decrease the rating by 5 milliwatt. It's 5 milliwatt for every degree Celsius. So if you are operating at 26, instead of 625 milliwatts, now your maximum allowable power will be 620 milliwatts. That is the meaning of the power derating. Physically, it may look like this. This is from a company known as Fairchild Semiconductor, 3 terminals, collector, base, emitter, and this is a general purpose one. Other characteristics, when it is off, which means cutoff region. In the cutoff region, how much is the breakdown voltage? 30 volts. On characteristics, when the transistor is on. Some spec sheets, they write beta. Some spec sheets, they write this thing, H sub FE. The one that I will circle now. H sub FE is also written instead of beta, but this is actually same as beta. You can see it is between 50 to 150 without a unit. Beta is a parameter that is sensitive to temperature changes. When temperature is changing, beta also varies a lot. What else can we see? So normally I don't ask questions from here, but I want you to know what is the meaning of a power derating curve and how to calculate the maximum allowable power when the temperature is increasing. If the temperature is decreasing, you don't have to do anything. It doesn't mean that you're gonna get extra. The limit that is given to you is already that limit. If you want to test a transistor in the lab, there's a curve tracer. If the transistor is working properly, you put on the curve tracer, it will show you the characteristic curve that we just studied. Digital multimeters, some of them have transistor testing capability. In my lab, the multimeter I use, it can test a transistor's functionality. If you don't have the transistor testing function, you can use an ohm meter. If you put a positive probe on the base terminal and negative probe on the emitter terminal, you should be seeing a low resistance. For a functioning transistor, this is a common emitter. You can see it's on the ground. The base emitter junction will be forward bias, which means you have a low resistance. The base collector junction, you would see a high resistance from base to collector. Current doesn't flow from base to collector. That would be the reverse bias one. So it is corresponding with a high resistance. Some of the examples of physical construction of transistor, there are so many different models. You might find one or more of these in the lab. The white dot is, in this case, the white dot is the base terminal, I believe. So before we go to the next part, I must tell there are 3 parts of studying a transistor. This is also true for the next chapter, next type of transistor. In the first part, we discussed the basic construction and terminal names, some formula for the transistor. In part 2, we do the DC analysis. And part 3, we do the AC analysis. So we are already in part 2, the DC biasing. What does it mean to bias? Biasing means applying DC voltage to a transistor in order to turn it on so that it can amplify AC signal. When I say signal, the signal is a waveform, AC. The final job of a transistor is to amplify AC signal. Either you increase the voltage or current, but the BJT is not any magical device. If you connect directly an AC input and you are trying to take an AC output, you will not get anything at all. You have to provide the DC voltage because the amplification is actually a result of energy transfer. And the energy transfer is happening from the DC power supplies. What is the average of a symmetrical AC waveform?
0.
0. So Really, there is nothing. If you try to input an AC and output an AC, the average power will be zero, if you think about it. The power is being provided by the DC source. It is also responsible for the energy transfer, and that is in turn responsible for any increase in voltage, current, power, etc. That's why you need the biasing. Oftentimes I ask this in the exam, why you need biasing. Now I would like to do a small exercise with you, a conceptual exercise. A IC versus VC graph is shown in front of you, okay? And then there are 4 black dots on the screen, if you can see. Point A, B, C, and D. Any of these can be your operating point, but some are not okay and some are the best. Some are maybe not too ideal. I'll go to the next student, which was on the line. So last class, I stopped with Mr. Thirawut. Next one would be Mr. Napatra.
Yes.
Do you see the 4 dots, A, B, C, D?
Yes.
If I ask you to pick an operating point, which one will you not pick? Which one will you not pick?
D.
You will not pick D, okay?
Yes.
Anything else? What about A, B, C? Can you tell me your reason why you said you will not pick D? What is your concern?
Like D is almost like to a limited limit operation.
Yes, it is quite close to the output power limit, that curve. So
Yes.
if there's any disturbance in the circuit, maybe large swing of the AC input, you might go beyond and then you might burn it. So your answer is correct for not picking D. How about Mr. Pakon? Anything else in this graph that you want to avoid? Is Pakon here?
Yes, I'm here.
So your friend, he said he will not pick D. It is one of the correct answers. There are so many answers here. Anything else that you do not want to pick from these, the remaining 3 points? Which one will you pick? I mean, which one will you cancel? Between A, C, and B, which one you want to throw away? Have a close look. I want you throw away B.
C.
Your friend already picked D to throw away. So I want you to pick another point, which you will not use. I want you to pick an operating point, which is in the active region, and the transistor will operate properly. Which one else are you going to throw away? Still thinking?
I think C.
Okay, Rajay, can you answer this?
Yes, Achan. Like, I will choose A, Achan.
You will throw away A, right?
Yes.
What is happening at A? Can you see? All of you can see what is happening. A is the intersection where you have 0 volt and 0 current. So really the transistor is not operating there. It is useless. You can throw away A. Now we have 2 points left, C and B. It looks to me that both are in the safe zone. But what is the best among these two? What is the better one? Chonikan? Is Chonikan here? Okay, what about Michelle? Michelle and Chonikan, are you not here, any one of you? Phil, are you here?
Yes, I'm here.
Okay, Phil. Between B and C, which one you think is the better one?
I think B is the better one.
Do you have a reason to justify your answer? Your answer is correct.
C is closer to the saturation and cutoff point.
Okay. That is a valid reason. There's another reason. Let me explain to you the other reason why. C is close to saturation region, so you might go in there. But also notice the slope of the line where C is here and slope of the 30 microampere line where you have B. If you keep increasing the voltage, C is almost a flat line. You're not going to have much current gain. But B, you can see, even though the degree theta or the slope is still small, but it's larger than the bottom line. If you keep increasing the voltage within your safe limit, you have a current gain. I mean, if you can pick a 30 microampere base current, operating base current. From there, if you keep increasing voltage, the corresponding current gain will be larger. And the ultimate job of an amplifier is to make gain for voltage and current. So B is the best point here. The second best is C, D is dangerous, and A is useless in this example. So everyone understands what happens here, why I pick like this. Three operating regions. Now it is explained in more details in terms of biasing. What happens in the active region? We are assuming certain type of configuration to explain the active and cutoff region. So in an active region, the base emitter junction is forward biased. Let's see if we can go back to the previous picture. Where shall I go? I think it's a common emitter thing. In the active region, see, I believe it is referring to a common base NPN. Base emitter junction here is forward biased actually. Plus, minus. So let's come back to the slide. The base collector junction is reverse biased, which is also true, active or linear region. For the cutoff region, you will have the base emitter junction reverse biased. In the cutoff region, you don't have current. And the base collector junction should also be reverse biased or forward. I think it's reverse. For saturation region, both junctions will be forward biased, base emitter and base collector. It is kind of hard to memorize and understand if you don't have a corresponding picture. But the idea is for the three regions, the junctions, the two junctions are biased in different ways. You see, for the saturation, both are forward biased. For cutoff, both should be reverse biased, although it's not written. And for active, one is forward biased, which means the input side is forward biased, and base collector, the output side, has to be reverse biased. I started by talking about biasing. Biasing means the act of applying DC voltage or DC input to your transistor so that it can turn on and amplify signals. But how do we do the DC biasing? We have to construct circuits. In the circuit, you'll have a DC source, you have some resistors, you have the amplifier itself, and then maybe some other element. Not maybe, definitely you have to have capacitor. There are four ways 4 basic ways or 4 basic circuit constructions for DC biasing, which we study in the course. The first one is called fixed bias. The second one is emitter bias. The third one is voltage divider, and the fourth one is DC bias with voltage feedback. But in the book, it says the name is collector feedback. They are the same circuit. Since we assume that you already know the circuit theory and we already introduced the basic characteristics of P-N junction, current and polarity, we'll go a bit fast from here. But it is still within the time frame and course outline. So fixed bias. What happens? First, look at the transistor. Is it PNP or NPN?
PNP.
NPN.
NPN. When the arrow not pointing in, it is NPN. Pointing away is NPN. This is an NPN. You see the 3 terminals, base, collector, emitter. The vertical line of the amplifier always the base. What is happening? VCC is the DC bias, the DC source. It is connected with the resistor RB. Why RB? Because this resistor connects with the base terminal. That's why we call it the base resistor RB. And then from VCC on the other side, you can connect with the collector terminal C. And this resistor we call the collector resistor RC. For the emitter, we put directly on the ground. Fixed bias, the emitter has no resistor. And then we have to connect the signal, right? Input signal is an AC signal. It is connected with the capacitor and then to the input base side. If you want to take the output signal, you take the output from the collector. This is a common emitter fixed bias. You take the output from the collector, join a capacitor, and then measure the output signal. The current that flows through the base resistor, it comes from the VCC. We call it the base current IB. Also, because of the parallel connection, the current coming from VCC will pass through RC. We call this collector current IC. And when the transistor is on, you have emitter current IE equals IB plus IC. You also have to account for 2 voltages, plus, minus. From B to E, there has to be a VBE, 0.7 volts always in this course. And then VCE from collector to emitter terminal. Now, there are 2 loops in the circuit. Let me zoom out a bit. I'll pick the yellow marker. There's an input side of the transistor and then the output side. Which one is the input side? Which one is the input side? Any clue? For a common emitter, input side is base. So the base has a loop. You can say KVL loop. VCC minus IBRB minus VBE equals 0. This is one loop. What about the outer loop? This is the input loop current, input loop equation. If you want to find IB, what is the equation? VCC minus VBE divided by RB, from what I just said. Outer loop, VCC minus ICRC minus VCE equals 0. That is the output side equation. Can everyone follow? Also, when we do the DC analysis, capacitor, you have to make open circuit. Why? Why the capacitor is open circuit? You don't think of capacitor and AC anymore. We are now strictly in the DC analysis. What is the current equation the current that flows through a capacitor. IC equals, do you remember what is IC? IC equals what? Nobody remembers? C times dV over dt. Do you remember now? Capacitor current. This current is C dV over dt. Now, AC voltage varies with time. What about the DC voltage? Does it vary with time? Does the DC voltage vary with time? Does it change with time?
I don't think so.
No, it's a constant voltage. If you take d dx of a constant or d dt of a constant voltage, you get 0. D dx of constant is 0. So 0 current, which means open circuit. And why we take constant voltage? We are doing DC voltage analysis. We have not come to AC yet. AC will be next week. So the input base emitter loop, you can rewrite the circuit like this: VCC minus IBRB minus VBE equals 0. Never forget the VBE. From this, you know the value of IB. VCC normally is given, VBE is 0.7. From the circuit, you can see the value of resistor. Why do we need IB? Come back to this graph. Back to the characteristic graph. You need to know IB because you need to see which IB you are going to take. Is it 10, 20, 30 microamp or in between? You have to find the output operating point based on the established input base current. That's why the first step, find IB. Output loop, what did we say? VCC minus ICRC minus VCE equals 0, which means it is the same equation. It means VCE equals VCC minus ICRC. And IC is beta IB always. What are we trying to find in this equation? The bottom equation, what does it tell you? It is the load line equation, isn't it? If IC equals 0, let's say IC equals 0, what is the value of VCE? IC is 0, what is the value of VCE?
BCC.
Yes, when IC is 0, VCE equals VCC. And when is IC 0? Cutoff point. Now think about the saturation point. When VCE equals 0, what is IC? When VCE equals 0, what will be the value of IC? What's the equation?
VCC over RC.
VCC over RC. Now let's look at this graph. Here, first we found the cutoff point when IC is 0. When IC is 0, you saw VCE equals VCC. This is our extreme point. And then for saturation region, where I said VCE is 0, IC is IC max, VCC over RC. This is the load line determined by the network. You can move this point by changing the value of the resistor. Now, what is IB? Why did we take this point? IB we analyzed from the beginning using the equation VCC minus VBE divided by RB. Let's say you find IB at this point. We call it IBQ, the base current at operating point. Your load line joins this base current line, this is your Q point, operating point. If you project a line straight down, this point here is VCEQ. That is your operating output voltage. We call it VCEQ. Okay, I have to try one more time. VCEQ, or the output voltage, the exact output voltage. Similarly, once you found the Q point, you can project a line on the IC axis. This value is the output collector current at your chosen operating point. So we already discussed when VCE is 0, saturation current. What is the meaning of VCE 0? Can we look at the transistor? If VC, this is C, this is E. To make the voltage between C and E 0 means it is like shorting the 2 point. When you short the 2 point, you have the maximum current. The transistor is saturated. That's why it's called the saturation current, IC sat. And when IC is 0, obviously nothing flows. If you put a probe, the VCE will be the same value as VCC. And the base current is here set by value of RB. You can change the input DC bias VCC as well, but normally we don't do that, not very convenient. If you have a variable resistor RB, you can keep changing the IB value. And IB is the one that controls VCE and IC. So IC equals beta IB. Again, to remind yourself that the BJT is a current control device. What happens if you change VCC? How will it affect the Q point? We know that, let's say we have a fixed IB. This value is fixed. This is our IB. This is the line that we choose. Our first load line is here. We found that saturation current is VCC1 over RC. Now we will change the value of VCC. We decrease the VCC. The value will decrease because VCC is in the numerator. So the load line will now change from the first VCC to the lower VCC. The load line have to be drawn to the left. As you can see, the Q point 1 is now the second Q point. If you further decrease the VCC but keep the resistor constant, this is the third point. It means if you decrease VCC, the operating point will move left along the base current line. What if I change RC? Keep the VCC constant, but change the value of RC. So this is VCC over RC. If you lower the RC, it means you increase the saturation current. So R3 is the lowest one. R2 is the middle one. R1 is the lowest value. R1, R3 greater than R2 greater than R1. R1 is the minimum resistor value. When you divide something by the minimum, you're going to get the maximum saturation current. When you increase to R2, this value will decrease. You have the second one. Further increase resistor, the saturation current will be even less. Our base current is fixed, so again, the Q point is moving along the base current to the left. You can do another way. If you change IB, what happens? How do you change IB? Maybe you can, we keep the VCC fixed here, RC fixed. What is the other way? IB equals VCC minus VBE divided by RB. So we can change RB to get a new base current level. If you change IB, what happens to the Q point? The Q point will move either up or down on the graph. It will go to a different base current level. It cannot move left to right on the same IB line because IB now has changed. Any questions? Until now? Do you have any questions?
I don't have right now.
Okay, I'm running a bit ahead, but I would like to just explain this emitter stabilized bias, and in the next class we can do some analysis. I also want to tell you one very important information. In the first circuit you saw fixed bias. You had RB, RC, but you had no RE. If you put a resistor now on the emitter terminal, we call it the emitter stabilized bias circuit. What happens? I probably mentioned to you that beta is a parameter that changes with temperature, is temperature sensitive. Let's say your beta is 50, maybe because of changing temperature, it now became 90. What happens in that case? If you have for 50 beta, you will have a certain output voltage VCE and certain output current IC. If your beta doubles, your output voltage and current can change by a lot. Maybe the output voltage now changes by almost 100%. Output current also changes by maybe 70–80%. So that's an unstable situation. If you put the emitter resistor, when the temperature changes, you will still get the beta changing. Maybe beta doubles again, but in this case, the output change, the change of the output voltage and the change of the output current will be much less compared to what you would see for a fixed bias. That's why it is called emitter stabilized bias circuit. So the output swing is less. It is more stabilized. I will show you some examples with numbers comparing a fixed bias to the emitter stabilized bias. Show the number when the beta changes and you can then see. It is a worked out example in the book. In the next class, I can do that. But when I ask the question to the student why the emitter bias circuit is more stable, they give me, most of them give me this answer, because there is a resistor on the emitter. That kind of answer gets 0 mark. It does not get any mark. I know the emitter bias has an emitter resistor. It's a very obvious answer. Don't give me the obvious answer. You have to explain why it is more stabilized than the fixed bias. Because the equation becomes such that the output, which is also dependent on beta in some way, it becomes somewhat less dependent. So do the DC analysis. What happens? The input small vi, it is an AC signal. It is an AC signal. The output, you are also expecting an AC signal. Not working properly. Okay. So we are doing DC analysis. Forget about the AC at all. Capacitor, forget about the capacitor. It's not there. We'll only focus on the middle part. What is the input loop equation? Now you can tell. Input loop equation, same. VCC minus IBRB minus VBE minus IERE equals 0. So here, now there's a resistor, and never forget the VBE. Even though it is not given, you have to have a voltage drop between B and E. I'm gonna just sketch that. output side loop, VCC minus ICRC minus VCE minus IERE equals 0. So you have ICRC voltage drop. Never forget the VCE. It has to be taken into account. So from Kirchhoff's voltage law, you see VCC minus IBRB minus VBE minus IERE equals 0. This is the base emitter loop. Since IE is exactly beta plus 1 IB, instead of using IE, you can convert the equation to an IB term. And then you isolate RB in the equation, IB. It becomes VCC minus VBE divided by RB plus, in the bracket, beta plus 1 whole bracket multiplied by RE. Any questions? Is this part clear? Simple mathematics. This is the IB equation. IB equations, I think, are given on the formula sheet. So nothing to memorize. You don't even have to memorize if you can solve with KVL. If you solve with KVL properly, you will not make mistakes. How about the emitter collector loop? I say it in a different way, but it's correct. VCC minus ICRC minus VCE minus IERE equals 0. Here all the signs are flipped, but if you multiply 0 with a minus sign, still the same. If we approximate IE to IC, you can write VCE equals VCC minus IC times. So IE you can write as IC in the bracket RC plus RE. Can everyone follow the analysis? Can everyone follow?
Yes.
Okay. Also VE equals IEREY. This is E. This point is E. From E to ground, this ground voltage is 0. So according to Ohm's law, the voltage drop from E to ground is IERE, correct? If you want to find the voltage VC, not VCE. VCE is from C to E, and VC is exactly at point C. What is that? It is the source minus all the voltage drop. It is VCC minus ICRC. You can see here. I'm highlighting, oh no. Right hand side. Also, you can say using double subscript notation. If you write VCE, it means VC minus VE. So move VE to the left hand side. You get VC minus VE equals VCE. You can sometimes solve the point voltage using double subscript notation. What is VBE, for example? VBE is VB minus VE. That is VBE. All right? So VB, just like I said, without even looking, I wasn't looking. If you take VB minus VE, it becomes VBE. So VB equals VBE plus VE. Also, if you look at the point B, let's go back to the circuit, actual circuit. VB is here. The point B is at this node. It is corresponding to the voltage drop from VCC to this point at the bottom of resistor, VCC minus IBRB. But it is also VBE plus VE, because from B to ground, there is another loop you can consider. So that's how you solve. Now you can find IB, and then where is your load line equation? This is your load line equation. This one. You can determine, let's say when IC is 0, VCE equals VCC. When VCE is 0, what is IC? It is VCC divided by RC plus RE. Just same as the previous one. But you have now an added resistor RE. So stability, it is a condition where you find the currents and voltages remain fairly constant. It doesn't say constant, fairly constant over a wide range of temperature and better values. If you add Re, it improves the stability. And how it improves, I told you, I explained to you. If some of you are recording, you can play it back. Also, I explained this part. If VCE is 0 volt, which means from C to E is 0 voltage drop, it is equivalent of shorting the CNE. When you short, all the current will go through, maximum current, that's the saturation current. And here is the analysis using the load line. We know from that equation, when IC is 0, VC equals to VCC. When VCE is 0, IC became VCC divided by RC plus RE. You already found IB in the first step, so take that corresponding IB, get the Q point, drop it down. This is VCEQ, and drop it horizontally. This is ICQ. Next bias we're not going to study yet. Let's see if I have any examples that I can show. I'm going to your Teams page and looking at the class notebook. Let's see if I have an example of stability analysis, which you don't have to calculate because it should already be done. Series diode emitter, stabilized bias. Okay, not there. Self-bias, JFET, emitter stabilized. Beta variation. We have a few minutes. I can let you go a bit early, but I would like to show you this. Give me a few moments before I can switch the screen. Okay, I'll switch the screen now. Can everyone see the notebook? Can you see the notebook, the class notebook?
Yes, we do.
Yes.
Okay.
Yes.
This is a worker example in the book. Let me increase. This is a fixed bias. As you can see, you have RB, RC, there is no RE. Initially, we started with a beta of 50. Now, when beta changes because of temperature, it became double, 100. See what happens to IC and VCE. IC changes from 2.35 milliamp to 4.7, more than double. The output voltage dropped from almost 7 volt to 1.6 volt. That's a huge swing. This is the effect of changing beta on a fixed bias circuit. Now, if you do the same thing with the emitter stabilized bias, what happens? Now you have an emitter bias circuit. You have an emitter resistor Re here, 1 kilo ohm. Start with a beta of 50. And then assume that because of the change in operating environment, beta has doubled. As you can see, IC changes, but about by 1.5 times, not more than 2 times. And VCE dropped from 14 to 9, which is less variation. Not ideal, but if you compare the first case and the second case, the emitter stabilized bias is more stable than the fixed bias. And then we will study more biasing circuits, which are even better than the emitter bias, because the output almost does not depend on beta. That is for the next class. I would now like to take the attendance for today's class. Is Min Luin Wu here? He's from section 555, just joined. Some days he can come, the other days not. Balan?
Yes, Ajahn.
Irawut? Patra?
Yes.
Bakong?
Yes.
Rajay?
Yes, Ajahn.
Tonikan?
Yes ค่ะอาจารย์
Michelle? Michelle here? You?
Yes.
Silicon. Miss Silicon?
Yes
Salute?
Yes, sir.
Yu Cheng? Yu Cheng? Yeah?
Yes, Ajahn.
Patampong?
Here ครับ
Ungsu?
Yes, sir.
Martin?
Yes, John.
Rawit?
Yes.
Ayut?
Yes, Cap.
Jimma?
Yes, sir.
Kunyuan?
Yes, I'm here.
Tawat?
Yes, Ajahn.
Yapeng Wang?
Yes, teacher.
Lenny?
Yes, I'm here.
Dipop?
Yes, I'm here.
V2?
Yes, yes.
San An?
Yes.
Waramet?
Yes.
Nawawan?
Yes I'm here
Natapop?
Yes, I'm here.
Warapat?
Yes, I'm here.
Ataya?
Yes teacher
Ichayapong?
Yes sir
Amchan?
Yes, I'm here, sir.
Iradon? Sanapong?
I'm here.
Tit?
Yes, sir.
Asin?
Yes
Ukaina?
Yes teacher
Rin?
Did you say Sirin?
Sirin is here. Is Piradon here? Piradon?
Yes, I'm here, teacher. My internet not very good.
Okay, what about Yu Cheng?
Yes, teacher. Yes, teacher.
And the last one I'm calling again, Michelle?
Yes อาจารย์ can you hear me
Yes. And Min Luin U? Min Luin U?
Ajahn, did you call Silipop?
I call everyone, City Pop, everyone. Everybody is present except for one student from 555. See you next week. Next Tuesday, your
Teacher, teacher,
who's speaking?
Xuan Yuan, I didn't hear you call my name.
Xiang?
Xuan Yuan.
Shun Yuan, I call you, yes. I
didn't
gave you
hear.
attendance.
Okay, thank
Ajahn, you didn't call my name, but you already checked my name, right, Silipop?
Who?
Silipop, Ajahn.
City Pop, yes, I call your name. And you also said yes.
Okay, thank you, Ajahn.
See you on next Tuesday. Remember, your homework is due next Tuesday.
Yes, thank you, Ajahn.
Okay, the class is dismissed. I'm gonna close the conference call.
Thank you, Ajahn.
Welcome.
Thank you, teacher.
you.